I need to talk briefly about nitrogen in organic chemistry compounds as well. Nitrogen is another player when it comes to organic chemistry, and the simplest of the nitrogen compounds is when you take off one of the positions on nitrogen and put an alkyl group off of it. Now, if you remember from Lewis structures, nitrogen is happiest with a lone pair and three single bonds, all right? So you can take 1, 2, or all 3 of those bonds up with alkyl groups. And that's why you see that weird system right there. So the number of alkyl groups, it can be no more than 3. And if you have less than 3, then you'll replace them with hydrogens. So let's talk about one of the simplest families of alkyl groups, which are listed in the upper right. The first one is methylamine. The nitrogen, which is in blue, has 1 methyl group connected to it, and the other 2 spots on nitrogen are just taken up by hydrogen. There's a lone pair on that nitrogen right there. It's going to give nitrogen its distinctive reactivity and stuff. That would be methylamine. But the next one to the right, that nitrogen has 1 hydrogen and 2 methyls, so it's dimethylamine. And finally, you can replace all of those hydrogens with alkyl groups, i.e. trimethylamine. Very, very cool. In the lower left-hand corner, that animation is for ethylamine, 1 ethyl group connected to nitrogen. These amines have nasty, nasty odors, and I never recommend that you are around amines if you can help it. Honestly, most of the amines are weak bases, and that's why they're really good about cleaning things. We're not used to smelling them and stuff, which is crazy. An amide is something I will never ask you any questions about, but I want you to hear this name because amide and amine sound really similar, and honestly, on a quiz, I thought amide was the same as an amine, and I didn't do too well. So anyway, if you hear amide, the name, or even better, if you see the capital N, like right there, that means that you've got an amide. And an amide is another nitrogen compound. It's got some kind of alkyl group next to it, but it also has a carbonyl. And if you put that carbonyl, that C double bond O, next to the nitrogen, you have all kinds of reactivity issues. So just realize this is another real powerful kind of condition. In the lower right, you see an NN dimethyl. That's because the nitrogen has 2 methyl groups connected to the nitrogen. There's a lot of stuff you can do with it. And again, I'm not going to ask you anything about this, but I want you to know that an amide is different than an amine, and that's important to me. This is an overview of the different families we've seen. So we've seen, for example, how a double bond between 2 carbons is an alkene, triple bonds alkyne, alcohols and ethers, aldehydes and ketones, carboxylic acids. Ester is one I'm not going to ask you about, but I want you to know. Amine, the nitrogen groups, and amide, which is another one I won't ask you to know, is the nitrogen connected to the carbonyl. Alkanes are the simplest ones, so don't forget those. Those are just carbon-carbon single bonds, and they're also really important. So again, if you kind of understand how this works more or less, that's what I want you to do. And I definitely want you to know about alkyl groups and how they're the building blocks of all these things, and definitely know that amide and amine are different, and ester and ether are different. You're in good shape.
To visually reinforce the fact that members of a homologous series, such as we see here, differ from each other by a specific structural unit, we use molecular models. Here, for instance, is the tetrahedron of carbon, a model of methane. In order to turn that model into ethane, we add another CH3 group to the end by substituting for a hydrogen. If we wanted to go from a propane to an ethane, we would remove that specific member of the homologous series, a CH2 group. Reconnecting the carbon atoms, then we're back to our ethane. Models can be used that are commercially available, but if they're not available, gumdrops work just as well.
If you take organic chemistry one day, I would find it essential, all right, not recommended, but essential that you purchase a model kit, all right, because as you can tell, there's lots and lots of different structures, and each structure has its own variations. Those different variations will have their own geometry, which leads to differences in reactivity, and it's really, really cool to have a model set. At the time of making this video, the model kits are roughly $20 on Amazon. You can get any of them that work, but wow, they can sure be helpful. So again, I highly recommend it. And in addition, all of those cis-trans things with double bonds, those can get kind of weird. The model kits will help you out. Eventually, you'll get into the chirality, like the mirror images we talked about in chapter 19. And oh my goodness, the model kits are so invaluable. So highly recommended. And yes, you can use gumdrops, but I intended to eat all my gumdrops, so I never had my good model kit. So I finally just bought one so I wouldn't have to eat them. But anyway, that's a personal thing. So there we go, off my high horse. I've told you what I think. Okay, the remaining slides in this chapter are just informational. I want to give you some examples of reactivity, and I'm not going to ask you any questions on this in Chem 223. However, if you go into organic chemistry, you'll kind of get an idea as to what you're going to get yourself into, and it's totally doable. It's just kind of crazy. Reactivity is, of course, a much bigger part of the chemistry, the organic chemistry year, but it's all stuff you can do. I'm also going to talk real fast about polymers. Polymers are plastics, all right? And that's another really important part about the world and organic chemistry, but everybody tends to gloss over, which is unfortunate. So the rest of the slides, you can just stop now and, go watch TV or something. But anyway, or you can go on and learn more about this stuff. Either way is cool.